Welcome back to the course in nuclear medicine physics. Today we're looking at both iterative and statistical reconstructive techniques used in medical imaging modalities. This will lead us to the most popular used algorithm in actual clinical applications today, the maximum likelihood expectation maximum algorithm. In contrast to the analytical reconstructive techniques that we looked at in the past lecture, these statistical and iterative techniques provide a new formalism for how we can reconstruct images, and they've had a significant impact on the field because of it.
So in this talk, we will move on to iterative reconstruction. We talked about analytic reconstruction in the previous talk, and now we're moving on to iterative reconstruction methods. The problems that we have in analytic reconstruction, the approximations made in analytic reconstruction are the following: that the projection data are assumed to be line integrals through the object. It's the radon transform just assumes a line integral. All right. So if you have deviations from a line integral, for example, in PET you may have photon non-collinearity, you may have positron range, or for both PET and SPECT you may have intercrystal scattering and blaring and all these things. The kind of a radon transform cannot take that into account. Also, the noise in the measured projection data is not really modeled properly. Again, when you think about the radon transform, you think of a noise-free scenario, and the projection slice theorem that we just talked about doesn't think about noise. It just assumes we have a noise-free world, and it arrives at those beautiful mathematics. And also, as you saw, the projection slice theorem works by the assumption that you have infinite projections around the subject. And, all three of these are issues and problems in analytic reconstructions. And iterative methods, especially statistical iterative methods, and the statistical especially refers to the second part where you're really thinking about the noise. These kind of models can tackle these better. So looking at the system matrix, what does it mean? What is a system matrix? And so this is one of the key concepts in statistical and in iterative image reconstruction for us to understand what a system matrix is. So the system matrix essentially describes the relationship between the object and the camera. So it's a data acquisition process, right? So you're thinking, if I have an image, if I have an emission from this pixel or voxel, what is the probability that I will detect it along a certain line here, projection here? Okay, so each element of the system matrix represents the probability that an event which originated in a certain voxel is detected along a certain projection. So this could be a projection for a gamma camera, as in SPECT imaging, or it could be a line of response for PET imaging. So, it's linear algebra. This is what the representation is. And you write it out like this. And the point here is a system matrix does not have to assume a perfect line integral. Often, the most simplified model does is it is a line through the object, and you sort of write it out like that. But technically, you could model like blaring phenomena in it, etc. So, and also other things in it. So it accounts for geometry of the problem, but also you can model other things in it because it's a probability of detection. You could put attenuation here. And this, by the way, as also we've said before, is the reason SPECT has become quantitative, because attenuation correction in SPECT is very difficult. And through this formalism, you can make it happen. You can model the attenuation for any given pixel or voxel. You can calculate the attenuation, and you can basically put it in here in the system matrix. So it's a very powerful approach to the problem. So if you write it out like this, so the projection data, this is a 1D measurements, so all projection values. So we model the system matrix as a 2D matrix, and then X is your image. Again, you're modeling your image, even though your image is 3D, but you kind of put all the pixels in the image, all the voxels in the image, into a 1D array. So just for this way of writing things. So this is, so again, even though this is a 1D vector, but that doesn't mean your image is 1D. Your image is 3D, but or it could be 2D if you're just thinking of a slice, or 3D if you're thinking across the body, but you write it out in a 1D vector just because of the linear algebra formalism, but you're not oversimplifying. So you write it out like this, and your job is to really solve for X, right? Because you've measured the projections. Presumably you understand what the system matrix is. The more you think about it and the more physics we understand, the better we can model this. As people who do image reconstruction, we have to understand the physics of image acquisition so we can improve this modeling in the system matrix more and more. For example, again, as we've said before, we could put attenuation in here. We could put resolution degrading phenomena in here, resulting in so-called resolution modeling or resolution recovery or PSF modeling, as we've talked about in different contexts. But what's the most trivial way of solving this? Well, just taking the inverse, right? So if I have p is equal to a times x, then the inverse will give you the x. The problem is this matrix is extremely large. Why? Because think 3D here, and think actually a small image. In practice, we're looking at now, 128 cubed or 256 cubed of those kind of orders, give or take, right? But let's say 64 cubed kind of image. And you're projecting it onto a let's say gamma camera that's 64 by 64, and let's say you're rotating it at 64 angles around the patient. So the size of your projection is 64 by 64 at 64 angles, so this is 64 cubed, and your image reconstruction matrix is 64 cubed. So this thing is a matrix that is 64 cubed by 64 cubed, okay? That's a massive system matrix, right? I remember that even in the 2D, where it used to be like 120 or 128 square by 128 square, I remember there was a time where MATLAB couldn't handle that. Now, of course, you can do more and more, but the point is these are massive numbers to store, right? That's problem number one. So in practice, people look for another approach. And secondly, who says that A has to be even a square matrix? I mean, here we made it simple, but why should we have to have the same number of elements here and here? In practice, in fact, A is not a square matrix. You may have an underdetermined problem or an overdetermined problem where for example, an underdetermined problem, or let's say an overdetermined problem, you may have actually more projections than pixels, right? For example, in 3D PET, when you have all those oblique angles, you end up over-determining the problem, which is good because it helps you reduce the noise in the reconstructions. But A is not even square, so this is not even a meaningful term because you cannot invert a non-square matrix. So we have to think of this differently. For example, think of the least squares framework. Least squares framework is based on a model, a Gaussian model of noise, okay? So whenever you're doing a least squares, you can actually, the original formulation can be the Gaussian model of noise, where you're modeling this term to be Gaussian. And if you model this term to be Gaussian, the difference between this and that, when you minimize that difference in a least squares sense, you're actually maximizing the probability of having the data that you're having in a Gaussian sense. So when you're doing this when you're asking the question like this, you're saying, what is that image X whose forward projection AX is close to my measured data as much as possible, and maximizing the Gaussian likelihood of me having obtained this kind of a data set. Okay, so you're minimizing that. And so how do we do this? Well, if you take, if you do linear algebra calculus, for example, for example, setting the derivative of this to 0, because you're trying to minimize this, you arrive at this formula, and then you just take it through and you work it out, you get this. This is guaranteed to be a square matrix here. A transpose times A. And then you're taking the inverse of it and you take this. This is known as the pseudo-inverse estimate of X. Okay, or pseudo-inverse estimate, pseudo-inverse estimate of X. So remember, this is not meaningful necessarily because A may not even be a matrix. But this is meaningful. And this is also known as the normal equation. Okay, so inverse is meaningful, as I just mentioned to you. Still, however, the problem with this algorithm is that this still is a massive matrix. So inverting it has the same problem. You're dealing with a massive matrix that you have to store and to invert and things like that. So we still have that problem, but at least the equation is sound now. It's a meaningful equation. So I want to ask you, I want to poll you here. The pseudo-inverse estimate or the normal equation that we just showed, which one is it? Is it analytic, non-statistical, analytic, statistical? Is it an iterative algorithm but non-statistical, or is it an iterative algorithm and a statistical algorithm, or based on a statistical model of noise? Think about it. The equation we just showed, which is this equation. Which one is it? Which one of these frameworks is it? Because we can think of algorithms as either analytic, or iterative. And we can think of algorithms as statistical based on a model of noise, or non-statistical, which means not really based on a model of noise. All right, so answers are coming in, and most of you are inclining towards the last one, which is half correct. It is statistical, but it's actually not iterative. What I showed you is statistical. It's based on a model of noise, a Gaussian model. It's least squared is based on a Gaussian model of noise, but it is not an iterative algorithm. It's actually an analytic formula that you just saw. So here, so this is not an iterative formula. It's just a closed form analytic formula. There's no iterative updates. It's a formula that you can implement and get the answer. But it is statistical because it is based on a least squares model and Gaussian model of noise. Okay, so the correct answer is B. Now, coming back to this, remember this, and based on which we came up with that analytic formula, the normal equation, the pseudo-inverse, but that had the inverse on top of it, and that required, storing the matrix and inverting it. But there's another way to do this. There's an iterative way of optimizing this, and we won't go through the proof. But actually, if you do this algorithm, this is not a closed form algorithm because you have to keep updating it. You start with an initial guess for X. It could be all ones. Then you forward project it, take the difference. Then, A transpose means the back projection. So A, system matrix forward projects, but if you take its transpose, it actually does the opposite, back projection. And then you add it with this term, and you update and update. Notice once you get an answer that makes sense, then your forward projection of your answer should be very close to the actual measured data. And so this term should technically become smaller and smaller, and therefore this update will become less and less. So at some point, these two are supposed to converge, right? So here we have an equation that looks like this. This is actually known as the Reblur Van Sittert algorithm. It's used in different contexts. In fact, not commonly even for tomography, but for non-tomography. Like, think of A as just a blurring operator. If I give you an image that has been blurred, how do you de-blur it? So think of A as a square matrix where all it does is it takes an image to itself but blurs it out. So you could actually do this to de-blur the image. And notice there is no matrix inversion. Okay, so you do not have to do the inverse. And so you do a forward projection, take the difference, back project. And the beauty of these things is you don't even have to store the system matrix. Forward projection is an operation that you can actually do on the fly. You take an image, you throw it, you for example, it could be a blurring operation, or it could be like a forward projection operation where you're like doing the radon forward projection, which you could do on the fly as opposed to having to store the system matrix. But the point is that this does not have the inverse, and you can actually implement this more easily. So here's another question for you. The Reblur advanced iterative approach that we just showed, is that analytic, non-statistical, analytic, statistical, iterative, non-statistical, or iterative statistical? Okay, so which one is it? Yeah, so most of you are answering, some of you are inclining for C, but most of you are saying D, and D is correct. D is correct. Why? Because it is statistical. Why is it statistical? Because it is based on the least squares concept. It is based on the least squares concept, and you're trying to minimize this. So this is the derivative of this term being set equal to 0. You're trying to achieve this. What is that x that makes this term 0? Or what is that x which minimizes this term? So this is based on a statistical model of noise. You are thinking about noise as being Gaussian distributed, resulting in a least squares model. So it's statistical and it's iterative. Okay, so the answer is iterative and statistical. So we just realized that an iterative algorithm or a statistical algorithm doesn't have to be iterative. We showed an example, the normal equation, the pseudo inverse, where it's analytic, and we show another example, the Reblur advanced iterative algorithm, where it is, iterative, statistical and iterative. In the literature, sometimes you will see if A is a square matrix for like blurring operations only, that people may not have this term. So they call that just advanced iterative algorithm. So you drop this term out. But that is not statistical anymore. That's just some kind of a ad hoc equation people have used without this term. So that would be an example of an iterative algorithm that is not statistical because it's not based on this model. If you do it properly based on this model, you do have to have this extra term here, which is therefore the name reblurred. But again, this model is not really used in reconstruction for nuclear medicine, and the key reason is because noise in the projection data in nuclear medicine is not Gaussian. Were it to be Gaussian, this would be a good reconstruction algorithm to use, but it's actually not Gaussian. So yeah, so this formula is iterative, and it satisfies that mindset of iterative thinking. And what does that mean? You start with, okay, so this is a patient scan and you've made a certain measurement. This is fixed. You've already measured the projection data. Now you want to look for that image whose projection comes close to this. Well, you start with an initial estimate. It could be an image of all ones. You forward project it using the system matrix. You get some estimated projections. You compare it with the actual measure projections. Likely they will not be close in the first iteration because you start with a terrible guess, all ones. So these are going to be very different. So you compare them. In the case of Van Sittert, you take the difference between them. You compare them, and so you arrive at the error term. Then you back project, because this is a back projection operation. You back project that, so you get an error term. So this is kind of saying, oh, that was not a good guess. You have to really add this extra factor to it.
Yes.
You have to add this extra factor to it, and then do the update. Okay, so you get this extra term, and then you add to it. Yeah, so then you have this error term that has been computed, and you add it to it, and you just go through the steps, okay? And you go through this loop until that, you get a reasonable image. Now, historically, there have been other algorithms, especially you've heard of the ART, the algebraic reconstruction technique. And it feels kind of quite similar to something like the Vansittart that we just discussed. But it's not statistical. People weren't thinking about noise. They were just thinking, okay, I have a linear algebraic formulation. Rho is equal to, or P is equal to A times X. How do I arrive at a solution without inverting the matrix or doing those large inversions? So not thinking about noise. Is there a way to solve? Is there a way to solve those sets of equations? So people have come up with different algorithms, not necessarily focusing on the noise aspect of things. So here's an example where you start with an initial guess. It could be all ones. This would be a vector of all ones. And then you forward project, you take the difference, you do some kind of normalization, and then you may do some kind of a back projection, and then you update the image. So it feels kind of similar to the Reblur Vansittart, but it's a different formula. And again, historically, these have been thought about. There are different versions of ART, and then there's MART, which is multiplicative version of this, and there's SMART, which is simultaneous multiplicative. But the point is, these are algorithms that are nice in that they're iterative. You don't have to do that inverse, that large system matrix inversion, but they are not statistical. So throughout the years, they have kind of gone south or downhill because people have really seen that statistical formulas that really think about the noise more properly end up giving images that make more sense. So let's move back to statistical iterative reconstruction. The Reblur Vansittart was an example of that. These kind of approaches are referred to as statistical iterative, or sometimes referred to as model-based iterative reconstruction, where you're modeling, the noise. So you have a statistical model. And often, because they have been so successful, when people nowadays say iterative reconstruction, they predominantly mean statistical iterative reconstruction. So in the clinic, when we say iterative recon, we are doing statistical iterative recon. Okay, so that's good to remember. But again, not any iterative is statistical, such as the ART that we showed before, and not every statistical is iterative, such as the normal equation that we showed before. But in practice, typically nowadays, when people say statistical, they mean statistical iterative, and when they say iterative, they mean iterative statistical. So that's good to know. So let's talk about this more, because we talked about the Gaussian model of noise, but really in nuclear medicine, as we've discussed before, we're dealing with the Poisson process. And the formula for the Poisson process is given by this. So if you have a measurement P, just think of one projection, one line of response with P number of counts. If the expected, the mean number of counts is given by lambda, this is the probability of having obtained that many counts. So if this is the expected mean, the true mean, the probability of getting this many counts is given by this formula, which is which models the Poisson process. Now, how do we model the expected value? Now, think tomographics and forward projection. Well, the expected, the mean number of counts in the projection space can be given by this formula. So you're kind of casting the question like this. What is that X? What is that X, the true object value, whose forward projection, which is supposed to give you the expected number of events, is close enough to the actual measurements that you made. Okay, so hang in there. So this is we write it out like this. we get this formula here. And then because the Poisson variables are independent, this was just for a single bin, single projection, single line of response. But because if you have multiple acquisition, multiple lines of response, multiple projections, the point is that Poisson variables are independent. So the probability of getting all of those is essentially equal to the product of all these probabilities. So because independent variables, the probability of getting a vector of independent elements is equal to the product of the probabilities of each of those elements. So what does that mean? Well, so we can write out the Poisson likelihood function. So we basically take this formula, and instead of lambda, we write this formula. So lambda being the forward projection of x. So lambda is this mean value, the expected value for, let's say, a projection bin line of response, j. And then you write this formula for each of those elements, and then you do a product of those for this line of response, and this line of response, and this line of response, and this line of response. You multiply them because they're independent Poisson processes. So this is a Poisson likelihood function, which we would like to maximize. So the problem becomes, so in the Gaussian model, you are maximizing the Gaussian likelihood. And if you write out the Gaussian, it's e to the power of minus something, the error term squared. So maximizing that turns out to be equivalent to minimizing the squares, because there's a minus e to the minus something squared. Maximizing that is equal to is the same as minimizing that something squared. So that's a least squares method. But here you're maximizing this term, and we take the log of it just to simplify things. So this product becomes a summation, just like a Gaussian too. So you take the log of a Gaussian, and then that gives you that exponential term minus that term squared, and then maximizing that is the same as minimizing that term squared without the minus sign. So, so we want to maximize this Poisson log likelihood function, which is the same as maximizing the likelihood function. What does that mean? Intuitively, this is a likelihood estimation, and a number of you have seen this in other applications, in other courses perhaps. But what does that really mean? It means we want to pose a problem as follows. What is that image for whose forward projection, P, with a hat, or P bar, the measured data P is most likely to happen? Okay, so this sounds weird, but just hang in there. What is that X? Given what I've measured, what is that X value? What is that object whose forward projection, if I assume this is its forward projection, for that forward projection, the measured data set has the highest chance of happening? What is that object whose forward projection gives me a certain distribution that is the most likely explanation for the specific measurement that I made? So you want these obviously to be close to each other. You want that X whose forward projection gives you this. And it turns out, if you have just this function, if you have just this for a 1D problem, this thing is maximized when these two guys are equal. But in a product, you've got a whole bunch of bins, and you cannot make sure that this is equal to that everywhere. You're saying, what is that X whose forward projection gives me a certain mean expected projection that is close in a Poisson likelihood sense to the actual measured data sets, okay? So then you go through the math and you try to maximize the log of this. So if you write the log of that, it gives you a summation. Log of a product is the summation of the logs. And you write this out and you get an equation like this. And this equation is independent of this last term because the last term does not have X in it. It's independent of X, so it doesn't matter. because you're trying to maximize X. You're trying to come up with that X which maximizes this. So you come up with this term, okay, which you're trying to maximize. And we need an algorithm that arrives at the solution maximizing that likelihood function. And then I won't go through the derivation there, but there is a so-called expectation maximization formalism to do this kind of optimization. And applying that to this problem, you arrive at the so-called maximum likelihood expectation maximization algorithm, which looks like this. And this is probably, if you are to memorize and understand one formula in nuclear medicine image reconstruction, this is it. This is an incredible formula. The more you look at it, the more you learn about it. There's mysteries about it. There's so many things about it. I've looked at this formula for 20 years now, and it continues to engage me. And I'm not exaggerating. So the way this works is kind of like the Reblur advanced Iterative, but a totally different equation, but the concept is somewhat related. So you start with an initial image guess, you forward project it, but instead of taking the difference, you take the ratio. So this is the actual measurement. This is the estimated forward projection. You take the ratio. Ideally, this ratio should be 1, but especially early on, it won't be. Then you take the back projection. This is the transpose operation. If I were to write this in strict, instead of element by element formulation, if I were to write it as like a matrix multiplication, this would actually become a transpose. So this is a forward projection operation with the JI multiplying by the X. But when you go back so this is here you're summing over pixels. So this is forward projection, but here you're summing over projection. So this is a back projection. And so do a back projection, and then you multiply it by this initial image guess, and you arrive at a new guess. You can imagine that if this term becomes 1, if your forward projection becomes very close to the actual measurement, this term becomes 1. So you get a back projection of all 1s, and then this thing itself is a back projection of all 1s. So these two terms cancel out, and you say that the next update is the exact same as the previous update. And I've shown this picture before. It's the same idea, right? So this is just general. You start with an image estimate, forward project, compared with the measure projection, you arrive at an error term, back project, update. But specifically for MLEM, here you take ratios, not the difference. You take ratios, then you back project and do that normalization. The normalization is this term here, okay? And then you arrive at a correction image, and then you multiply that correction. In the Reblur advanced Iterative, you added it, but here you multiply it. You multiply this correction image by your initial estimate. That's this formula. So this term normalized by that term gives you the correction image, then you multiply by that term, and that gives you a new image estimate. So to wrap up, statistical reconstruction has a number of advantages compared to analytic reconstruction. First of all, projection data are not assumed to be line integrals. You have a system matrix. Inside your system matrix, you could do a lot of interesting things. It doesn't have to be a line integral. It could be modeling things like, for example, intercrystal scattering, detector blaring, positron range, and things like that. Noise is modeled in statistical reconstruction, not in all iterative recon methods, but in statistical iterative recon methods, it is modeled, which in the case of the MLEM or the OSCM, which I will talk to you about, which is just a variant of the MLEM, it is assuming a Poisson noise. And finally, you do not have to have an infinite number of projections or even a tremendously large number of projections. You could have less number of projections and still do a good job. So what is OSCM? OSCM is really MLEM, but acting in every iteration on only a subset of the projections. So for example, you may have let's say in PET imaging, you may have a total number of 288 angles, okay? Well, you could divide those into, let's say, 16 subsets, each of those subsets having 18 projections. So it's almost like you take out every 18 projections and or every 16 projections, and that gives you 16 subsets with 18 projections in each of those subsets. So then you're speeding up the MLEM because in each iteration, you're only looking at part of the data. So you don't have to back project the entire data. You only back project part of the data. And that was discovered by accident, actually, that it speeds things up. Each updated image is then used as an input, and then you move on to the next subset. So this is the MLEM formula, but in the OSCM, you only do the back projection at each iteration, not on the entire data set, but only on a subset of the data set. So each subset, each update takes much less time because you're only looking at part of the data. That ends up actually giving you nice image updates, and you keep cycling through the different subsets, and so that ends up giving you that. So subsets are just a part of the data. You take your full data set and you partition it into subsets, right, within that data sets. And then you only use those parts, those subsets for each update, and then you move to the next subset, and that actually ends up speeding things up. So here's an iteration, or here's an image showing the results of iterations. With MLEM, meaning you don't do subsets, you just do one subset, one big, huge subset. As you iterate 4 times, 8 times, 16 times, this is what you get. But if you now add subsets, and you do one iteration, full iteration, having gone through the entire data set 4 times, it's almost like you went through the data set once, but you've actually updated your formula 4 times because you first used a quarter of the data set, got an update, another quarter, got an update, another quarter, got an update. So by the time you finish cycling through your entire data, you already have a better image estimate. And so you see that with more subsets, you end up moving faster. And you could, of course, do post filtering, after you do the image reconstruction, you could do post filtering. So here, filtering means like post reconstruction, Gaussian filtering. Here's another example, just showing the effect of post filtering. So this is with the noise-free example, high counts reconstruction from a low count, so therefore high noise. So we tend to, after we do MLEM or OSCM reconstruction, we tend to do post smoothing in the clinic. This is extreme. Nobody does that for PET imaging, for example. So nowadays, typically people do post filtering maybe by, let's say, 5 millimeter Gaussian post filtering. One of the issues with MLEM is that as you iterate more, the image starts to look better and better. But after a while, if you iterate too much, the image may become too noisy. So MLEM OSCM reconstruction may become more and more noisy. So if you do extreme number of iterations, that may be a problem. That is a problem. So there are some solutions to that. So people may only use few iterations. Let's say in the clinic, we may do, for PET imaging, for example, we may do 2 or 3 iterations with, let's say, 16 subsets. So that means 2 times 16 number of updates, maybe 30, 40, 50, give or take, depending on the scanner, depending on many criteria. We may iterate that many times, but then we stop. Also, when we stop, or if we iterate more, we could use more and more post smoothing to deal with the noise. But then there's a whole different approach to this, and we alluded to this in a previous talk we gave, the first talk we gave on image reconstruction. When you can do Bayesian reconstruction, we can add your beliefs into the system, into the formulation. So you move from likelihood formulation to the maximum a posterior or Bayesian formulation, where you're saying, I don't want to just maximize the Poisson likelihood. I also want to add a penalty term that, for example, penalizes things based on my belief. For example, that if I believe that nearby voxels should really be similar, if I believe that nearby voxels in my final image should be quite similar to each other, if they're not, I'm going to penalize that. So you can add that prior model and arrive at a maximally posterior reconstruction. And we showed some examples of that. The pitfall of MLEM is that to get to that, I first have to make a statement. This is actually not a pitfall, this statement. MLEM enforces image non-negativity, meaning a reconstruction with MLEM, is always going to be positive or non-negative. Okay, now that's actually a good thing. It makes sense because you're reconstructing counts, and the number of, the radioactivity is a positive thing. Radioactivity it cannot be negative. So that's a good thing. However, when you're having very low statistic studies, let's say you're only having, few events that you're back projecting, let's say tens of thousands or hundreds of thousands of events, not millions of events that you're having. Or if you're looking at parts of the image where the counts are too low, like in cold regions, because you cannot have negative numbers, you may not be able to cancel things. For example, imagine a really, really cold, like a cold region. Well, if you have noisy reconstruction, noise kind of wants to do this. So it can definitely become positive, but it cannot become negative because this MLEM does not allow negative. So it's kind of in filter back projection, the positives and the negatives may cancel each other out. So you put a region of interest on that cold region. On average, the positives and negatives cancel out. You may get a value close to 0. But in MLEM, you're going to get positives because of the noise, but you cannot have negatives. So you end up actually having an overestimation bias. You end up actually overestimating the signal there. Now, there are variants of MLEM that try to tackle this problem that I'm mentioning here. But at the end of the day, you need to be careful with this issue. You do need to have sufficient number of counts. If the number of counts become really low, you will have problems. So this is something to be careful about. But ultimately, and I think oversimplifying here a bit, but ultimately, people have observed that in typical reconstructions, statistical iterative methods tend to outperform analytic methods. Again, typically in typical scenarios. So that's why the majority of image reconstructions nowadays in routine reconstruction are being done with iterative reconstruction, where for example, the same level of bias, you may get less noise, or for the same level of noise, you may get less bias. So to conclude, I would say that as beautiful as analytic recon approaches to the radon transform have been, statistical model-based approaches provided a totally different formulation and paradigm to the problem. And they've had significant impact. So you had this beautiful formulation. This is a great lesson in science. And then something else showed up that was totally different and ended up really taking us to a different space. So it is entirely possible that there might be new formulations in the horizon that might also possibly replace the existing ones. I mean, for example, in the AI world, people are thinking about deep neural networks, and perhaps those can be used for this problem and image reconstruction problem. But the point is, there have been fantastic developments in image reconstructions, that there have been different paradigms applied to it. And in this paradigm, in this very successful paradigm of statistical iterative recon, nuclear medicine has actually been at the frontier. And in routine clinical practice, statistical iterative recon algorithms have really been applied for quite a long time now, and increasingly so. And it is more and more in recent years where the value of this has been realized in other practices, such as in CT imaging, where switching from filter back projection type algorithms to statistical recon has been a major frontier in the CT world, for example, in more recent times, resulting in advanced, improved image quality and or reduced dose and things of the sort. So, yeah. Thank you for your attention.